A Gaussian distribution has a very interesting property, which, in my opinion, is the prettiest, the most wonderful, and the most important in everything that has to do with the Kalman filter. If you multiply two Gaussians, then the result is also a Gaussian. Now, I sense that you are not in a "oh," so let me say it again. If you multiply two Gaussians PDF, the result is also a Gaussian PDF. And in this video, I'm going to try to do two things. The first is to explain why this property is correct. And the second is to explain why this property is so important. Now, in order to explain this property, let's go back to the one-dimensional Gaussian distribution. And if you remember, one of the reasons that we love so much the bell curve or the Gaussian distribution is that it's described by only two parameters, mu and sigma. One can think of the mu or mean as the best guess, and one can think of the sigma as the uncertainty or the spread of the curve. With mu and sigma, you can compute everything there is to know regarding a Gaussian distribution. So, in order to explain this property, I will first give an intuition. Let me give you the following scenario. Assume that I have some vehicle and I have no idea where it is, but I'm guessing it's at point which I call mu1. Okay, now I'm not convinced, therefore around mu1 I have uncertainty, which is described by the variance sigma 1 squared. Now, if you remember from the previous section, this distribution is also called a prior. Why prior? Because this is the first distribution before we get information from the surroundings. Now, I turn on the GPS and it say, listen, you're not at mu1, you're at mu2. However, the GPS isn't accurate either. Therefore, the GPS is also described with uncertainty, which we'll define as sigma 2 squared. Now, what is the best guess at this point with regard to the position of the vehicle? So your initial guess was mu1 with sigma 1 squared. Your measurement was mu2 with sigma 2 squared. What are you going to do now? Now, this is rather a tricky question because if my sensor is really accurate, you're probably at mu2. And if the GPS is awful, so I guess the best guess is still mu1. But our world is not binary black and white. It's mostly gray. Therefore, our sensor is probably semi-accurate. And so the prior distribution is also semi-correct. So if your intuition says that you are around a point mu3, which is between mu1 and mu2, you are correct. Mu3 will be higher or bigger than mu1 and smaller than mu2. So again, if your prior distribution said mu1, but your sensor said mu2, you are probably in between. But here we get to the most surprising property of a Gaussian distribution. The question is now, what will be the new uncertainty, or what will be sigma 3 squared? Will it be higher or lower? Now, the interesting thing is that sigma 3 is going to be lower. In other words, the new PDF or the new Gaussian or the new posterior estimate will be more accurate than the prior distribution and more accurate than the sensor. Now, it seems counterintuitive and I can say it stems from the math, but let me give you an intuition. Why is it true? So let's say that my first Gaussian looks like this and the second Gaussian looks like this. So now it is easier for most of us to feel that the posterior will look something like this. Why? Since mu3 is the region where PDF1 and PDF2 overlap. So in a way, they both agree on mu3. Therefore, mu3 must be more accurate. My point is that the first drawing is just like the second drawing. Why? Since a Gaussian distribution spans from minus infinity to plus infinity, so at this point, mu3, the two PDF also overlap. So let's move to the math. The first PDF is described here. This is the equation. The second PDF is described here. Now, what is the result of PDF1 times PDF2? What happens if I multiply those two functions? And the answer is that if you do the math, you get another Gaussian distribution that can be written like so, with mu3 and sigma 3 squared. And how do you derive mu3 and sigma 3 squared from mu1 and mu2? Watch. Mu3 equals mu2 times sigma 1 squared plus mu1 times sigma 2 squared divided by sigma 1 squared plus sigma 2 squared. And this is pretty logical if you think about it, because the smaller the sigma, the better the mu. Again, the smaller the sigma, the more accurate the distribution. Therefore, the new distribution needs to be closer to the accurate distribution. So as sigma 1, for example, approaches infinity, the new mean will approach mu2. Why? Since mu1 is very inaccurate. And as sigma 1 approaches 0, which means that mu1 is spot on accurate, mu3 will approach mu1. So what happens to sigma 3 squared? It equals 1 divided by 1 divided by sigma 1 squared plus 1 divided by sigma 2 squared. And if you're familiar with electronics, this is what we call a parallel connection between two resistors. And this equation has two interesting properties. The first property is that sigma 3 squared will be always, but always, less than sigma 1 squared and sigma 2 squared. Always. The second property is when sigma 1 equals sigma 2, then sigma 3 squared equals half of sigma 1 squared. In other words, when we multiply two Gaussian distributions, when each one has the same uncertainty, the new Gaussian distribution that we'll get will have a variance that is half of the original variance. We shrink the uncertainty by 2. This is a very unusual property because it lets us take a prior Gaussian distribution, multiply it with a data from the sensor, which is also a Gaussian, and get a new Gaussian distribution that is described yet again by 2 parameters and 2 parameters only. But the new posterior distribution will be more accurate than the prior distribution and the sensors. This property also allows me to take any Gaussian sensor and use it no matter how noisy it is, because the new posterior estimate will be always more or maximum equals to the prior distribution. I can utilize any sensor no matter how noisy it is.